Uh, Good afternoon. A very warm welcome to everyone joining us today. As we gather here today for the final day of our Atal online 6-day faculty development program on emerging frontier in energy, climate and sustainability, we carry with us not just knowledge but also renewed commitment towards shaping a sustainable future. Over the past 5 days, we have collectively explored critical issues, innovative approaches, and transformative technologies that drive energy efficiency, climate action, and sustainable practices. We have witnessed a wonderful combination of ideas, technologies, and sustainable practices that will inspire us in our teaching, research, and professional journey. Today's lineup of session is truly special with thought-provoking discussions, innovative technologies, and visionary insight. Now, we begin the session 11, which will bring yet another significant frontier into discussion. The topic for this session is Emerging Power Plant Technologies, Supercritical, USG, CFB, and Waste to Energy Plant. To guide us through this insightful session, we are privileged to have with us a distinguished expert, Mr. Deepta Sundar Malik, Director of Development Consultant Private Limited, Kolkata. Mr. Malik holds postgraduate degree in mechanical engineering and has more than 45 years of experience in conceptual design, layout, equipment selection, and detail engineering of various systems related to various plants, particularly thermal power plant and petrochemical plant. His specialization is in the field of cogeneration, waste heat recovery, and bulk material handling system, including cross-country conveyors. He successfully executed projects of national and international importance on behalf of NTPC, Indian Navy, Nuclear Power Corporation, State Electricity Board, ISRO, Stone and Webster Corporation, USA, Toyo Engineering Corporation, Japan, and various customers of Saudi Arab, Abu Dhabi, Jordan, etc. He was nominated as member of various committees of Indian standards to develop various IS standards, also associated with many World Bank, Asian Development Bank funded
क्या
projects.
विशाल जी?
He has number of publications in various Indian and international journals and conference proceedings.
ठीक है जी.
He was a visiting faculty for bachelor's and masters of engineering courses at Jadavpur University, Kolkata in the Department of Power Engineering for the last 20 years. He was also visiting faculty at BITS Pilani, an external examiner for review of ME thesis for various universities. With his vast expertise in modern power plant technologies, he will guide us on how supercritical, USG, CFB, and waste to energy plants can transform the energy sector while addressing sustainability challenges. Let us extend our hearty welcome to Mr. Malik and invite him to share his insight. Sir, we are eagerly looking forward to your valuable session and the wisdom you will share with us today.
Yeah.
Sir, now you can share.
আমি পাওয়ার পয়েন্টে রাখতে চাই। ব্যাক করাটা okay. Good afternoon. Good afternoon, everybody. And my lecture topic, Madam has already introduced. And I have been working for more than 45 years. And during this long tenure, just a minute. Madam, am I audible?
Yes, sir, you're audible.
Yes. I myself have worked from great fire boiler to fluidized bed boiler to subcritical boilers to supercritical. In this all journey, I was involved on behalf of the company. So I can share some first-hand experience, whatever I had gathered. To start, the today's scenario is like this, that today we have in our country about 480 to 490 gigawatt of power generation, out of which we are very proud to say that about 50% is contributed by renewables and remaining 50% by thermal power plants. And out of this, again, about 90% of thermal power plants are being contributed by coal-fired thermal power
After
plants.
giving some electric current, those
Okay.
parameters only it is
So
getting
I
reduced.
request
This
participant
will
to
not,
please
it
mute
will
their
not
mic.
report to mission. Hmm.
So you need one parameter only.
Several.
Will you please keep mute? Otherwise, it will be disturbing to others. Okay. So, one very surprising fact is this, that although only about 45% of the total power generated is contributed by coal-fired power plants, but energy-wise, it contributes 72 to 73% of energy used or consumed by the consumers. That means coal-fired power plant has a very strong role to play even today. Okay, and it has been calculated and estimated that this role will continue for at least next 2 decades, if not 3 decades. Though renewable, more and more renewables are being pushed into the grid, but unless the storage system is really modernized to make it affordable, it is felt that not more than 45 to 50% of renewable can be pushed at any moment so as to ensure grid stability. So that means next 2 to 3 decades, we have to depend heavily on coal-fired power plants, what we have been doing for the last 40, 50 years. There is no respite from that. Although coal-fired power plants are considered as one of the very dirty power plants because it emits a large amount of CO2. And it is a fact also that considering the overall GHG gas emission in the world, 25% is contributed by coal-fired power plants alone. So that means coal-fired power plants are really dirty. But at the same time, coal-fired power plants are reliable and they are the backbones of the industry wherever coal is available. Wherever gas is available, naturally gas power stations have taken the lead role. But considering our country's situation, coal-fired power plants will be there. So our target should be how to make it high efficient, how to make it low emission, which is called HELE, how to make it high efficient and low emission. And with that in mind, there have been various developments over the last 20, 30 years, and gradually the utility power plants have shifted from subcritical to supercritical to ultra supercritical to advanced ultra supercritical. In the same way, to reduce the emission, circulating fluidized technology has come, and also new fuels have been developed. New fuels means waste. So waste to energy is another very relevant chapter in today's scenario. My lecture will contain all these three components. That is our journey from subcritical to supercritical, CFB, and waste to energy utilizing municipal solid wastes. I know that I have limited time, so I have prepared the slides accordingly. And sometimes I will skip one or two slides because some of the slides are heavily inclined towards mechanical engineering. And I know that most of our listeners are from interdisciplinary, not only mechanical, or from all the departments. So I've made it in such a way that anybody can appreciate the concept. Okay, so we start first with subcritical to advance to ultra supercritical. Now, steam power journey is a long journey. The first turbine, if somebody says that what is the first turbine in the world, that was developed in the 1st century AD, which is called Hero's Wheel, where you can see this thing where steam is being generated and it is being released in two opposite directions. And so it gets a torque and it rotates. That is the first turbine developed by man. Then gradually steam has been developed and James Watt has really come as a pioneer, and he developed the steam engine in 18th century AD. Then a steam turbine has come up because so far it was reciprocating. Now steam turbine has come up, which is a rotating machine, and ultimately supercritical. This is the long journey. We started from AD, even 1st century AD, even you do not ignore that. But there has been very rapid developments in the last 3 centuries, which has made it happen that the steam engine to modern supercritical steam turbine. And in the front of boilers also, there has been very rapid changes about, if you remember, the loco boilers. Those were basically smoke tube boilers where the hot gases used to go through the tubes and water was in the sail side. So that was the first type of boiler developed in 18th century or even in the early 19th century. And then gradually water tube boilers came into place, and subcriticals were developed and supercriticals were finally developed. By the way, let me first introduce the words subcritical and supercritical. Subcritical boilers are those, I have explained in a later slide, which is operating at less than 222 kg per square centimeter pressure, because that's a magic point. So that I will explain. And supercritical boilers operate at pressure more than that, more than the critical pressure. So there are advantages, and I will explain. And that is the discovery, that is the journey. And the turbine, as I told in the first slide, that it is Hero's turbine is the first turbine, which is actually a reaction turbine as per mechanical engineers' language. And there are impulse turbines, which was developed even before that. And then modern turbines look like this. And so this is the full journey of development of turbines, which is the prime mover. Now, for those persons who are not belonging to mechanical engineering department, let me give a very small recap that what happens in a coal-fired power plant. In a coal-fired power plant, boiler heat is applied in the boiler, water becomes steam, that steam goes to the turbine, it produces some power, and the exhaust is given to a condenser, which is again condensed by circulating water system. And this condensing water again comes back to the boiler through a boiler feed pump. This is the most, I will say, the preliminary cycle that man has considered. This is called Rankine cycle. And gradually, from this Rankine cycle, more developed cycles came up. What are those developments? Instead of expanding the steam from the boiler directly into the turbine, there can be some reheating. It can be expanded partly, then can be taken to reheater, and then can be expanded. This helps in two ways. Firstly, you get some more output. Secondly, when you are reaching the condenser, it will have better dryness fraction or lesser moisture. So that is one first set of improvement, which is called reheat cycle. Then further improvisation was made. That is, if instead of taking the entire steam from the boiler to the condenser through the turbine, if we take some steam from the turbine exhaust and utilize it to heat the feed water, then that is called regeneration, and that makes further improvement in the cycle. So these are the developments which were coming up, and then this is the reheat regenerative Rankine cycle, which is mostly applied in most of the subcritical plants, not only subcritical plant, even in the supercritical plants. And here the circuit is like this. The boiler produces steam. This goes, high pressure steam goes to the turbine. Turbine is in 3 stages: high pressure, intermediate pressure, low pressure. From the turbine exhaust, once again steam comes to the boiler. It is getting reheated, and then this reheated steam goes to the intermediate pressure, where it expands, and then it goes to the low pressure turbine, and then it goes to the condenser, and then subsequent heaters, and back to the boiler. So this is the very common modern day cycles we consider. And in in a picture form, this is my boiler. Coal is being fired here. Flue gas goes, it heats up, and steam is produced. It goes through the superheater, and then it goes to the turbine, and turbine through high pressure, medium pressure, and intermediate pressure. Again, it goes back to the boiler through a heater circuit. And in the flue gas side, this goes through the ESP, electrostatic precipitator, and goes to the stack. So this is the subcritical thermal plant with which we were used to for at least 30 years, 35 years. The efficiency of these subcritical plants, you are aware, that depends upon, in fact, it is governed by Rankine cycle efficiency, again, which is handicapped by Carnot cycle efficiency, which says that if there is a heat engine with its heat input at temperature capital T1, absolute temperature, and heat reject is capital T2, then the efficiency cannot exceed T1 minus T2 by T1. So considering the practical aspects, that T1 cannot be more than 550 degrees, 600 degrees centigrade, and T2, that is the temperature at which heat has to be rejected, cannot be less than about 40 degrees centigrade. So the most efficiency can be something about 60% if you just make the calculation. But again, for subcritical, we can never reach, because in the meanwhile, there are many other factors, and Rankine cycle is not the Carnot cycle. It approaches Carnot cycle, but it is not. So the efficiency we get in a subcritical plant is in the range of 35–36%. That is the maximum. In other words, 3 times the energy given to the boiler, out of which only 1 time is contributed towards electric production and 2 times is rejected into the condenser. This is a huge loss, but again, we cannot ignore or we cannot bypass the law of nature. We have to be satisfied with this as long as we are running coal-fired steam power plant. Now, how the supercritical concept came? From the Carnot cycle or from the Rankine cycle, one can calculate that higher the pressure, better the thermal efficiency, higher the temperature, better the thermal efficiency. In fact, temperature has a very significant effect in thermal efficiency, and pressure also has, but not to that extent. But if pressure and temperature both are made higher, then I am assuring of better efficiency. So that is the philosophy of supercritical plants. And supercritical has other advantages also that I will come later. Now, so far we are happy with the subcritical. Now, why we are so stretched? Because unless I can improve the efficiency, I am depleting the fossil fuel. Okay. If my plant is running at 35%, then the amount of coal I burn can be certainly reduced if the plant is run at 45% efficiency. So, depletion of fossil fuel is one major point which we need to take up, we need to consider. Carbon footprint, that is, if I produce 1 kilowatt hour of energy through a coal-fired power plant, around 0.7 to 0.8 tons of CO2, 0.7 to 0.8 kg of CO2 is generated and emitted into the atmosphere. My target will be to reduce it lower. Whenever there is a combustion, of course, C will be converted to CO2, and so I cannot get rid of CO2. It has to be emitted. But if I can improve the efficiency of the entire operation, then for the same megawatt, I will burn less amount of coal. So less amount of CO2 will be generated. So the CO2 footprint will be lower. Then water. For any power station, rough thumb rule is around 3 to 4 meter cube per hour of water is required per megawatt of power produced. So if I can have lower amount of better efficiency of the cycle, and I can produce the same megawatt by burning less amount of fuel and less amount of reject, then naturally water quantity will be also lowered. So these are the threats, sustainability threats, and since we cannot get rid of coal-fired power station, so we have to look at it that how we can improve the efficiency so that all these problems can be addressed and can be improved as much as possible. As I told you, the limitation of the subcritical power generation is lower efficiency. Cost of power generation, if the efficiency is lower, naturally cost of power generation will be higher, plant size will be higher, environmental impact will be higher, less flexibility. This is another point which is favoring heavily towards supercritical, low efficiency in part load. And one of the most important factor nowadays is happening that since a lot of solar plants have been installed across the entire country, and solar energy is available at a very cheap price because you don't have any fuel requirement for that. And therefore, during daytime, the priority goes to put solar energy or renewable energy into the system. So that during that daytime, the coal-fired power station has to run at lower load. But the moment evening comes, when contribution from solar plant becomes zero, then demand has not come down. On the contrary, demand has gone up. So
Sir, you are muted. Excuse me, sir. Sir, your mic is muted. Sir, excuse me, sir. Your mic is muted. Audio is not coming.
are you getting now?
Yes, sir. Yes, sir.
Are you getting now? Okay?
Yes, sir. Now come.
Okay. This I have already explained. That is subcritical. This red line is the subcritical stream line flow. It has gone through the liquid phase and then has become gaseous stage or steam stage, gaseous stage, and then it has come down. This is the typical subcritical stun. And this is the drum. In any subcritical plants, you have to have boiler drums. These drums have downcomers, and there are some risers downcomer system as well as riser system. So water continuously, water comes here, then it is in the furnace zone, then it becomes hot, so some steam is generated, temperature goes up, again it goes here. So this goes on circulating. This is the principle of a subcritical boiler. But at flue gas temperature, for a subcritical, you see that this is the steam line. Flue gas is giving heat to the steam line. And so you can see that at most of the time, there is a huge temperature difference. Now, one of the common theory of a mechanical engineering is this, that if the heat addition can be done with lower amount of delta T, then the efficiency of the system will improve and otherwise entropy will rise. So that is a common knowledge of mechanical engineering. And next, so Rankine cycle is now improved, that higher mean temperature, increase in boiler pressure, critical point is 374 degrees centigrade and 22 megapascal. I remember it in a very easy way, that 222, the 22 megapascal is roughly around 221 kg per square centimeter. To make my memory, I consider this 222 kg per square centimeter and above 374 degrees centigrade. So far, subcritical boilers used to run at around 160 kg, 150 kg per square centimeter. So that is from subcritical to supercritical. That's a big jump in pressure. Although temperature-wise, subcritical temperature used to be around 550 degrees centigrade. And now the temperature has gone up, but not to that extent, 576 to about 580 degrees centigrade. This is the limit of the supercritical boilers as on today. And I will skip these two. And this is the modern Rankine cycle. This is the modern cycle of a supercritical plant. you see that the steam doesn't go through the this liquid phase. It stays straightway, goes to the top phase, then comes down, then again reheat, then again reheat. Then there are some regeneration steams which goes to the liquid stage, and ultimately the circuit is like this. That this is the steam circuit. It goes from here. You can see that there is no clear-cut division between water phase and steam phase. That is the beauty of the supercritical. And what happens that the flue gas delta T between at any point of time becomes lower when we are following this curve instead of curve like this. So that is the basic fundamental, that entropy is not generated into the system. So this is the overall thing. There is no difference between subcritical and supercritical in this respect as far as the steam cycle is concerned. Their boiler is produced, it goes to the steam turbine. This is the steam, it goes to the steam turbine. Then after expansion, I reheat it once again, then goes to the steam turbine again, and then it goes to the condenser, and from the condenser it goes to the deaerator, heater, and back to the system. So this is the supercritical. Only difference you see here, you don't have any boiler drum, because there is no difference of density, no difference, clear-cut difference between two phases. Everything is it starts from the liquid phase and ends in the steam phase, but there is no clear-cut division what we are used to in subcritical. Now, one important factor I must discuss, that is, what is the as I told, that in a downcomer there is liquid from the drum to the upper drum to the lower drum. There is liquid, and the liquid has a very good heat transfer coefficient. So whatever heat is there in the furnace, the liquid phase immediately takes it away. So if there is no such division between liquid phase and the steam phase, then how the heat transfer can be that much? Because if the heat transfer doesn't take place, then what will happen, that the metal temperature will be higher and higher, and so it will ultimately melt. So that was the challenge for any supercritical boiler, and that challenge has been overcome by making the supercritical boiler tubes specially designed. There are two designs. One is that one is that one is that you have a rifle design, and one is that basically you have a spiral design. In other words, whenever water is passing through the tubes, it goes through a swirling route. The purpose is this, that the heat transfer coefficient has to go up so that the tube doesn't get overheated. So that was the basic fundamental difference of a tube system, water tube system, of a supercritical boiler versus subcritical boiler. And there are circulation versus once through. Supercritical boiler is basically once through system. So I am giving the circulation, then I am giving the different types of tube design which is available in the supercritical technology. I am not going through all these figures and parameters differentiating between these two, subcritical and supercritical. I am going through this. This is very important, that subcritical has a temperature is roughly around 550, 560 degrees centigrade. But most important point is pressure is around 160, 170 kg per square centimeter. Supercritical, the pressure is around 250, 260 kg per square centimeter. And you will see that the temperature is around 560, 570 degrees centigrade. Ultra supercritical, you have even higher steam temperature, 650 degrees centigrade. So there has been a very marked difference of tube metallurgy So to make it happen, that to go it to 650 degrees centigrade, and ultimate target what man is achieving, man is trying to do is advanced supercritical, and you will see the rise in efficiency from 38% to 42%, from to 45% to 50%. At this moment, I tell you, everybody, that if you want to install a power plant, you will not be given permission to install subcritical power plant unless it is a captive power plant or cogeneration power plant. For utility power plant, you have to go to the supercritical power plant, because country cannot allow you to run a system with lower efficiency. Ultra supercritical, we are doing, our company is doing in 1 or 2 places. And advanced ultra supercritical is first coming up by NTPC, and we also by Adani, and for the Adani projects we have been involved. And look at the CO2 intensity. For subcritical, it was 880 kg or 0.88 kg per kilowatt hour. For supercritical, it has come down. For ultra supercritical, this is further come down. For advanced ultra supercritical, it has further come down. It is no wonder, because the efficiencies are going up. So per kg of coal, you are getting more amount of energy, useful energy, and that means in the reverse way, the same amount of electrical energy is produced by lesser amount of coal, so lesser amount of CO2. So these are the major advantages of supercritical. And supercritical, as I was telling, the supercritical can take up the change in load very rapidly. This is another advantage. In subcritical, you have a drum system in between, so it has a huge inertia. So it cannot take up the ramping up and ramping down very fast. But supercriticals have comparatively lesser inertia and can take up. So this has been a very major point in view of today's flexible operation, which says that during daytime you have to make your thermal power plants at lower load, and during evening time it has to be it has to be done at a higher load. And whenever there is a cloud formation, that means you get a huge fall in the from the solar system, but your demand is constant, and therefore your backup system, that is coal-fired power plant, it has to ramp up very fast. So all these requirements also favor utility of supercritical boilers. It is not only efficiency, it is not only lesser amount of CO2 generation, but its capacity or its capability to increase, to respond to load situation, ramp up and ramp down very fast, makes it an unique choice in today's scenario. You can get that the subcritical is around this 145 kg, maximum 37% efficiency, 540 degree. In the supercritical, we have already moved up and moving up and up and up. And now we are going to about 228 megapascal, means about 280 kg per square centimeter, 600 degrees centigrade, and efficiency 45%. And then we are targeting to around 700 degrees centigrade. There are enormous problems of creep and many other metallurgical problems, for which there are many researches being carried out across the entire country, across the entire globe, because it's understood that it has to be, temperature has to be higher and higher, so as to get higher and higher efficiency. But at the same time, the metallurgy should be such that after all, the plant has to be affordable to the common people. So this compromise has to be, is being done, and many efforts are being there across the laboratories to make material which can withstand up to 650, 700 degrees centigrade, and at affordable cost to the customer. In short, I have collected few figures of different installations. Now here, you just don't confuse. This is what is boiler efficiency. Boiler efficiency and cycle efficiency are not the same thing. Boiler efficiency means if you are putting 100 kg, 100 kilojoule of energy in the boiler, what actually it is giving to the steam. But cycle efficiency means if you are putting 100 kilojoule of energy to the boiler, what electrical work you are deriving out of it. So these two are different. Boilers are normally 85 to 90% efficiency, but cycles are about 32-3% to 50% is the ultimate target, depending upon whether it is subcritical, supercritical, ultra supercritical, or advanced ultra supercritical. And efficiency, you can see that these subcriticals are 33.78. These are actual plant figures. 660 is supercritical. 38.96 and 800 is another, again, supercritical with a little higher temperature profile. It is 40.68. I'm giving the figures of two very prominent power stations in the country. Both are by NTPC. For CPAT 660 megawatt, the main steam is 256 kg per square centimeter, and temperature is 540 degrees centigrade. Main steam is this is for bar 258. And temperature is around 568 degrees centigrade. So no wonder that BARD has a little better efficiency compared to CPAT. As days are changing, as new generations are coming, we are catching hold of better materials, and so we can go to the higher temperature. I have given a list of supercritical units which has been installed in the last 10-15 years in the country. It is not exclusive. There are many more things. As I told that nowadays, every plant is supercritical. In fact, we have got a few projects in the last 3-4 months, as I was telling, that about 88 gigawatt has to be pushed into the system through coal-fired plants, and therefore we are getting our share also. We have got DVC's Durgapur, DVC's Maithon, and DVC. Then we have got Adani's few plants. So lot of activities are being done nowadays. And with this, I stop here. Now I go to another theory, that circulating fluidized bed boiler. It's another innovation. What is a fluidized bed thing? If you have a fixed bed of coal, and if you push some air from the bottom, initially, if the air velocity is small, the bed will remain as it is. If the air velocity goes up, then you will see that the material will take the shape of a fluidized state, and it is sort of as if it expands in size. Then again, if you push more air at a higher velocity, not more air, at a higher velocity, you will see as if some bubbles are formed. This is called bubbling bed. Then if you even give higher air velocity, it will start turbulating, and then it is almost reaching the circulating fluidized bed state. And if the velocity is even higher, then what happens that it moves from the furnace and goes at the outside, and that is called circulating bed. So in circulating bed, I have to intercept the material again and then push back whatever is unburnt. So that is circulating bed. And this concept is not a very new concept. The first circulating bed boilers were developed in the year 1980s, 1990s. And if I remember, the first CFBC boiler was developed by BHEL and was put into operation in 1992. Since then, there are 4-5 companies in the country which have developed the CFBC boilers to a further higher level. They are Thermax, they are ISJEC, they are ThyssenKrupp, BHEL. These companies have developed. Sitar Vessel was a very good company, but they have closed. But circulating bed has now reached a stage where it is as reliable as a pulverized fuel fire boiler. and its efficiency is also quite high. Now, why this concept? Why do I take a concept of circulating fluidized bed when we are already had pulverized fuel fire boiler, reliable pulverized fuel fire boilers, which has been developed over 50, 60, 70 years? The concept has come because of two factors. One factor is that very often the pulverized fuel fire boilers are designed for a particular variety of coal. I personally am associated with this thing, so I know that when I have given a particular analysis of coal today, it is quite likely that after 10 years, the same ultimate analysis does not hold good. It is getting, if I take coal from the same mine, it is gradually deteriorating in its quality. And when such deterioration takes place, and it takes place quite rapidly, so initially my calorific value GCB was say 4,000 kilocalorie per kg, and after 6 years the coal I am getting has a calorific value of 3,200 kilocalorie per kg. The boiler cannot give the same efficiency. Boiler's efficiency lowers down in a PF boiler. But in a circulating fluidized bed boiler, the fall in efficiency is very nominal. For example, if in PF boiler, the efficiency falls down by 5% due to deterioration of coal quality, in CFBC boiler, it may be 1 to 1.5%. So that's one thing which is very, very important and very, very relevant to any power station. Second point, and that's more important point, is that in a boiler, in a PF boiler, your furnace temperature is about 1500 degrees centigrade, and SO2S converts into SO2, and this SO2 goes and it takes its exit from the chimney. Even though in our country the coal has less amount of sulfur at 0.5 to 0.6%, but even then the emitted flue gas I have calculated is around 1500, contains 1500 to 1800 ppm of SO2. Whereas ideally it should be around 300, not more than 300 to 400. And therefore, the emission possibilities are much more unless you install a full-fledged FGD system. If you are aware, considering this, in 2015, there was a regulation from the government that you have to install flue gas desulfurization plant so that the sulfur dioxide emission in the flue gas does not exceed 100 milligram per nm cube. Again, this is a very tough target. I don't know why 100 milligram was specified, whereas World Bank specifies 300 milligram per nm cube. But anyway, that was done. And there was a huge hue and cry, because now for every power plant, you have to PF based, subcritical, supercritical, you have to install the FGD plants. And this installation will create a capital expenditure of around 0.8 crore per megawatt and operating expense of around 40 paisa per unit. So everybody was very, very upset that what to do with that. But again, researches have been carried out, and it was found out that no, because Indian coals are primarily low sulfur coal, and therefore this full-fledged sulfur dioxide removal plant is not necessary unless the plant is located in a thickly congested area like NCR area, or very near to city of Calcutta, like that. But the advantage of circulating fluidized bed boiler, here circulating fluidized bed boiler has a beautiful advantage, because its furnace temperature is 850 degrees centigrade, contrary to 1500 degrees centigrade in PF boiler. 850 degrees centigrade is such a temperature where I can inject lime right into the bed and which can capture sulfur dioxide. And so in bed, sulfur dioxide capturing is possible with circulating fluidized bed. That puts it in a huge advantageous position. So, and also, NOx generation is another problem in any PF boiler, because again, I was telling that the temperature of the furnace is around 1500 degrees centigrade. So nitrogen and oxygen reacts and they produce NOx. And the NOx upper limit, though ideally it should be less than 400 milligram per nm cube, but the government has given a figure of 100 milligram per nm cube. There are a lot of confusions, a lot of demonstrations against that. But anyway, if we consider that 200 to 250 milligram per nm cube has to be rendered, it has to be kept, you have to have some denoxing arrangement in the PF boiler. It could be by changing the type of burner. It could be by putting some SCR catalytic reformer. It can be some other type of catalytic reformer. Whatever you do, it has huge amount of operating cost as well as capital cost. But again, here in the circulating fluidized bed boiler, your temperature is 800 degrees centigrade, 850 degrees centigrade. So your possibility of producing NOx becomes much lower. You know that Arrhenius theorem, where the temperature, how the reaction rate changes with temperature. It is an exponential theorem, and you can see that if the temperature falls down from 1500 to 800 degrees centigrade, maybe reaction rate will be falling down by say 40, 50, 60 times. So that means, in other words, the NOx generation is less. So these are the major advantages of circulating fluidized bed boiler. That one is that it can pick up almost, it can burn any type of coal, any type of fuel, not even coal. Number two is that it can have a desulfurizing arrangement at a very cheap method through in-bed limestone dosing. And denoxing is not required because NOx production is lower. So these are the basic advantages of the circulating fluidized bed boiler. The same thing, and as I told in the initially, that bubbling fluidized bed boiler is another type of boiler where the air velocity is little lower. And about 20-25 years back, almost all the boilers of fluidized bed design used to have bubbling bed. But again, bubbling beds are is good as far as the capacity is around 100 tons per hour. But when the capacity increases 100 tons per hour, circulating fluidized bed boiler has many added advantages, and so it is taken. And particularly for, I have given some comparison here. You can go through it. Because I'm running short of time, so I'm skipping something, and I will tell you something about circulating fluidized bed boiler. There are two types, as I have told, that circulating fluidized bed boiler takes up at a high runs at a higher air velocity for fluidization. So naturally, it goes. It takes in the flue gas. It takes a lot of coal dust also. Coal dust also, and this dust has to be Can you please mute, please? This dust has to be separated. There are two types of major variants. Both are developed by different companies in the world. One is hot cyclone. Here is the hot cyclone where the flue gas goes. Then here it is a cyclone. By cyclonic effect, the dust particles, coal particles get separated, and it goes comes back to the combustion chamber. and then the flue gas goes to the superheater, reheater, economizer, air preheater. Why it is hot cyclone? Because still here the flue gas temperature is quite high, say about about 600, 500 degrees centigrade. But in a cold cyclone, you see that heat transfer surface areas have been put into the system, and then after its temperature has sufficiently come down, it goes to the cyclone. So here temperature is 450 degrees centigrade. This is cold cyclone. Both the technologies are available. I can tell you that one big company, Lurgi, he follows cold cyclone, and Foster Wheeler follows hot cyclone. Both have their advantages, disadvantages, but these are the two types of cyclones which are very rapid. One advantage you can see that in the cyclones, your refractory thickness will be lower because the temperature is lower. In hot cyclone, your temperature is higher, so refractory has to be higher. And there is another type. I personally haven't worked with this system where the cyclone is located after in a U beam in the horizontal pass. I have not worked with the system, and I don't know which company manufactures, because all the companies manufacture either hot cyclone or cold cyclone technology. And here all the diagrams are there. And what there is a advantage, disadvantage of cold cyclone versus hot cyclone that I have given here. And I have now one can ask me the question that if CFBC has such good advantages, that it has a lower denoxing possibility, in-bed desulfurization can be done, it can burn any type of fuel. So why it is not used so extensively? Why this subcritical, supercritical, these words? This may be the question. I tell you that CFBC is a new development. As I told that possibly in 1990, the first CFBC boiler was installed in the country, and it is going through the process of transition. And at present, the highest, you can see that Thermax is producing up to 1,000 tons per hour. BHEL has producing up to 250 megawatt. ESJEC has produced up to 100 megawatt. Thyssen group has produced 125 megawatt. One can ask, why can't you increase the megawatt? Where is the challenge? The challenge is that you know that the air velocity has to be maintained around 5-6 meters per second. And if the furnace size, more megawatt means more heat to be generated into the market, into the furnace. So if the furnace size becomes extraordinarily large, the problem is that air across the entire cross-section of the furnace may not be uniform. And therefore, there may be areas where it is not in the fluidized stage at all. And there may be areas where it is in such a stage that it has gone to the transport phase, that it even doesn't get separated in the cyclone. Therefore, uniform air distribution across a furnace more than say 20 meter by 30 meter is a big challenge, and these challenges are being overcome, and higher and higher sizes are getting generated, getting manufactured in the world. And we look forward to that situation. Also, another thing I must say that CFBC boiler has efficiency of say around 84% compared to PF boiler, which has better efficiency of 89%. But at the beginning, I told that as long as your coal quality is consistent, PF boiler gives you better efficiency. But if you have a problem of getting consistent coal supply, and your coal supply can be varying with a huge margin, then CFBC boiler will give you ultimately better efficiency, considering the average factors. Another question that one can ask, that can CFBC boiler be reheat boiler? Yes, it can be. Can CFBC boiler be supercritical boiler? Yes, it can be. And there have been 3-4 instances already because many countries, particularly where coal quality is varying, they are targeting CFBC boiler to develop and take the role of PF boiler because of its inherent advantageous features related to emission. And 3-4 supercritical CFBC boilers have also been installed, not in India, but one in Poland, if I remember, one in China. So it has been installed. But again, I tell you that CFBC boilers are very acceptable as long as your steaming rate is not exceeding 200, 400, 500 tons per hour. In megawatt terms, 100, 125 megawatt. Beyond that, still we are in the development stage. Not only we, entire world is in development stage. So let us see that in next 5 years time where we can go. And the third and my last topic, and I have about 15 minutes time, so I will try to finish that, is something where I got the opportunity to work. So I thought that this is something I must share with all the faculties here. This is waste to energy incineration route. You know that at present we have a huge problem of municipal solid waste. Huge problem. I give you a figure that in West Bengal about 13,000 tons of solid waste is being generated, out of which landfilling is utilizing hardly 300, 400 tons per day at an average. But what to do with the remaining thing? It is getting stored, becoming hills and mountains. And that is the fate of the municipal solid waste. As more and more people are migrating to the cities and towns, this problem is increasing more and more. So there can be various routes by which municipal solid waste can be processed. But we were involved in a particular project where the municipal solid waste is being incinerated in a boiler and then the steam generated is going to the steam turbine and produces steam. And I tell you that I had been to the dump yard, I had been to the urban development office. It was very hugely welcome project because by virtue of this, we will be consuming about 976 tons per day of municipal solid waste. So that's a big relief to them because every day there's so much of municipal solid is getting accumulated that very often they will be completely eat up the land area and they have to look for another dump yard area, which is very difficult to obtain at this moment. So Indian waste, I will quickly go through all these things. That in India, we have around 160,000 ton per day generated. And we have high organic content. 70% of this is collected. So that means about, say, 112,000 tons per day is collected. Now, if I can convert it to landfill burden reduces. Energy from this waste can be beneficially used, and it supports Swachh Bharat and circular economy. Solid waste can be classified in various ways based on source, based on biodegradability, based on combustibility, based on compostability. This is very important. The best use of municipal solid waste at this moment, as I gathered from the dump yard and also from the government agencies, is preparing compost. which can be in fact sold at a price. But for doing so, one has to see that the organic waste has to be segregated, and those organic waste can be nicely nicely utilized to make compost, but not everything. And based on usability, these are the various classifications that I got. And the figures what I get from literature is that, as I was telling, that in Greater Calcutta we are having 13,000 tons per day. This figure is little old, but 13,000 tons per day is a huge figure. As I told you, that out of which hardly 200 to 300 tons per day are used for landfilling. So no wonder that every dump yard is getting filled very shortly, in a short time, and government is looking for some other areas, dump yard areas, and dump yards has its own problem. If you go past the dump yard, you can feel the smell and it's a horrible thing. So if we can utilize it, calorific value is not very bad. I'm habituated in kilocalorie per kg. So 5 megajoule per kg means around around 1,000 kilocalorie per kg. In Greater Mumbai, it is something like that. In Chennai, you have certain little better megajoule per kg. But underlying bottom line is that each of the plant, each of these municipal solid waste plant is getting stretched because their land areas are being completely occupied. These wastes can be converted into the various ways, of course, various ways. But one important factor is, as I have told before also, that the methods has to be affordable to the common public. The ultimate product has to be sellable to the common public. Not all are sellable to the common public till now, unless a suitable amount of research is being done and cheaper versions can be utilized. And these are the different types of MSW which we are getting in India, that biodegradable foodstuffs, recycled paper, tablets, plastics, inert stones and slate and other things. So waste suitable for energy production is solid waste with high carbon content, wastewater with high BOD and COD value, waste gases. We will concentrate on solid waste only. Waste characteristics is high moisture, low calorific value, high inert fraction. Again, I tell you that I have studied. You know, Tanner diagram. By the use of Tanner diagram, you can understand whether this is combustible or not. Fortunately, I made some laboratory experiments with some waste. So what we took sample from my nearby areas. Nearby, we call it Dhapa. Nearby areas, and fortunately, it is combustible. And incineration technology is controlled combustion, which produces heat, steam, electricity. By virtue, you have some ash, but volume reduction reduces by 90%. So 90% of the problem is solved. And incineration process is waste feed, combustion chamber, boiler, TG, flue gas treatment, ash handling. 1 ton per day MSW is around 400 to 500 kilowatt hour, which if you convert the amount of heat value and the convertible portion to electricity, you will get this figure, and you can get around 5,000 megawatt electricity in India if you can properly recover it. But the problem is that the flue gas control. Flue gas has many things, dioxins, lime. So you have to have some flue gas cleaning mechanism. But again, I tell you that the cleaning mechanisms, whatever has been developed, we are working with a Thermax boiler, and it gives the guarantee that whatever is the code standard, it can adopt to that. And the global experience is very popular in Europe, Japan, Singapore, in spite of stringent emission norms. And they can restrict low temperature heating. Normally they produce low temperature heating and can use for district heating. In India also there are a few plants, and we are doing a plant. Our client doesn't want that the name be disclosed in the public forum, so I cannot tell you officially. But I tell you that we have done the initial thing. We have made the layout. We have contacted SHUDA, that is Urban Development Agency, and have gone through a MOU sort of thing to supply MSW. So all these things have been done, and boiler order has been already placed. Layout has been already finalized, and that will produce steam, which will be utilized for electricity generation as well as steam for process heating. There are some regulatory frameworks which we have to follow, and we are certainly following these things. And institutional supports are there.
That will be introduced to you now. The app top
Challenges in India: low calorific value waste, poor segregation at source is one of the major points in our problem. And high capital cost and financing issue is another problem. And public opposition regarding the gas cleaning. People are not very comfortable with the gas cleaning, although there is a very clear-cut guideline of what the gas cleaning, what the outlet emission should be. But still there are concern of the local villagers and the local people. So these are the challenges. High capex. OPEX depend on waste quality. I tell you that we had launched a MOU sort of thing with the government. What they have told that they will be giving MSW at our plant, which is located about 100 kilometers from the dump yard, free of cost. So they are so keen to get rid of this waste that they are actually they have given us free of cost the fuel at MSW at our plant premises. Achha. Composting, I told you that whenever waste, particularly organic waste, is there, composting may be giving you better revenue. Biomethanation is okay, but revenue is not good. RDF and incineration is suitable for mixed MSW. RDF is something which is called refuse derived fuel. But from the municipal solid waste, you can improve the quality a little bit, and then you can put it in a form called refuse derived fuel, which is easier to burn, and you don't have to, which has a better calorific value of around 3000 kilocalorie per kg. So we are targeting RDF as our fuel, but in case the government cannot supply it, then even our boilers are suitable for burning MSW itself. And environmental concerns are there, fear of dioxin and furans. But again, I tell you that technology has been developed, and dioxin and furans release can be kept within the acceptable limit by the code. We had done this project. Waste generated in West Bengal is around 13,709 last year's figure. MSW collected is, and now here is the figure, that MSW comes to the dump yard in West Bengal, 13,356 ton per day, and only 667.6 is treated, and landfill is only 202.3 tons. It is in their literature, last year's figure. So what it means? It means a huge amount remains undisposed. And one little step what we are taking, that we are taking MSW from dump yard, we are converting to RDF. There are very standard companies who convert MSW to RDF, and the process is not very costly at all. Then incinerate in a boiler, production of a steam, converted to electric power and process steam. For this project, 800 I gave a wrong figure, 976 I told, no. 805 tons per day of RDF can be used beneficially, which means about 1,000 tons per day of MSW can be utilized regularly. And gross steam capacity from boiler 78 TPH. I assure you, whoever is listening, that I have visited a few 4 boilers running with this RDF and MSWs, and they are quite reliable. They are quite reliable. You can trust them. And steam pressure, we are generating at 552 kg per square centimeter. Steam temperature 405. Produces 12 megawatt electric and 30 TPH of extraction steam as process steam. Now the question that everybody will ask, how is the cost? I mean, whether it is because capital cost of these boilers are more compared to ordinary boilers. So what we have done that we have designed the boilers. We have specified the boiler to burn non-recyclable solid waste, rice husk, wood chip, bagasse as well. But we have not taken fluidized bed boiler because MSW, if MSW comes, which is a very difficult burning proposition, and therefore we have gone for a great fire boiler. Although if had we been assured of RDF all the time, we would have gone for fluidized bed boilers. And GCB of our design fuel is around 2000 kilocalorie per kg. And outlet gas composition, this is what the guaranteed figure by the boiler manufacturer, which is satisfying the norm of the country. This is the layout what we have prepared. I'm not giving the nameplate because otherwise the entrepreneur's name and address would have been disclosed. It was their request that till the time the project comes, we should not disclose it. That is a NDA clause, non-disclosure agreement we have signed. So I cannot give it. And this is a boiler, and the area is this big area is the RDF here. And from the boiler steam will be coming, and this is the fuel which will be coming to the boiler, and this is the gas cleaning plant, and it is ultimately being emitted through stack. This is the turbine generator building, and this is the plant, and we are starting the work very soon. Now, our capital cost, what we had submitted to bank is 148 crores for 12 megawatt plant and 30 tons per hour of steam. And what is very important is that return on investment is only 3 years. So you are not only helping the country, helping the municipality, but also if you can invest 148 crores of rupees, you are assured that your investment is recovered in 3 years' time, which I believe is a very, very good return. But of course, here the return shows a little better because 30 tons per hour of steam, what we are getting from the plant as well, in other than 12 megawatt electricity, we have considered the cost of steam as well. So, and that is what it should be. The bank has all, I have argued with the bank, and that has been accepted also. So ROI is not bad. That's what I mean. I think that any ROI, if it is less than 5 years, it is always acceptable. It should be acceptable. Over and above that, I have not considered any other benefits. Any other benefits means because I am burning ultimately some waste, so carbon trading I could have done, but we have not taken those figures here. It is the whatever figures is coming tangible, those figures we have put here, and in spite of that, it is quite attractive. Technology localization, cost reduction, greater private sector participation, source segregation. Source segregation is a very important thing, and if we can really segregate at the source, then there is a tremendous possibility. Unfortunately, in spite of governments and the municipalities' repeated request, I say that we as citizens, we have failed to do the segregation. They had given us color baskets, but very few of us really follow that. And if you can follow that, that gives a big advantage to the dumpier, who can immediately segregate. They don't have to put up additional forces to segregate. Conclusion is waste to energy via incineration can be part of India's solution, but needs integration with segregation. And of course, the plants have to be very strictly compliant, environmentally compliant. So with that, I end. Thank you very much. I am happy that I could finish within the time given to me. So if you have any question, please feel free to ask me. I will try to answer you in the next 3-4 minutes, 5 minutes.
We sincerely thanks Mr. Deepta Sundar Mallick for his insightful lecture on emerging power plant technologies, supercritical, USC, CFB, and waste to energy plants. He started his presentation by telling us about the power plant, its basic concepts. Then he also told us how we can improve the efficiency and lower the emissions of power plant. He also explained about different types of boilers and what are their challenges with the subcritical boilers. At last, he gave an overview on waste to energy in India and what are the challenges we face in India regarding this. His insights not only highlighted advanced technologies like supercritical and ultra supercritical system, but also shed light on clear and more efficient pathway such as CFB and waste to energy plants, all of which are pivotal to achieving our climate goals. Now we invite our participants to ask their questions and interact with our experts. We ask participants if they have any questions, they can ask.
Or they can write their questions to my email number. Is the email number is available in the recorded message? No, madam.
No, sir.
Okay, that I can submit you.
Okay.
But if you have any question, please feel free.
Do you have a question?
Sir,
Yes, sir.
sir, what is the maximum steam temperature limit at turbine inlet yet now?
Around 580, 585, 590. This is the range what we are following at this moment. Our target is to go up to 610 very soon.
Sir, which type of plant is called ultra supercritical?
Ultra supercritical, as I told, that when the pressure is around 270 kg square, I have given a chart also, that pressure is about 250, 260, 270 kg and temperature is around 595, 600 degrees centigrade. Those are ultra supercritical. And advanced supercritical is even higher up. It is targeting up to reach up to 700 degrees centigrade and 300 bar pressure.
So another question is that, sir, you have told that CFBC boiler is having a lot of advantages. Presently, in India, there is no CFBC boiler, perhaps.
No. There are plenty of CFBC boiler. If you see in the medium range, where say 25 megawatt captive power stations, so 25 to 50 megawatt, CFBC is more common compared to PF boiler. The reason is cost effectiveness is better, number one. Number two is that the smaller power plants, they purchase coal from various sources. So they are not very sure about the coal composition. And as I told, that PF boilers are susceptible or sensitive to coal quality, whereas CFBC is not. As long as it can burn, it will burn and burn with more or less similar efficiency. That is why the smaller plants, you have plenty or at least 100 plants which are being run, particularly in the range. Even right now we are working in a project in Botswana, which is being set up by Jindal. Jindal is the owner of the plant. Their Thermax is supplying 4 units, each of 150 megawatt, and 4 CFBC boilers, each of around 500 tons per hour. That is in Botswana, but is being manufactured by Thermax only, Indian company, Pune based.
Now, what is the maximum capacity of CBC boiler now?
Now it is around 500, 600 tons per hour. Thermax claims that they have the design for 1,000 tons per hour. That is converting to around 250 megawatt.
Okay, sir. Thank you, sir.
Okay. But as I was telling that it's a future sunshine areas. So, and the problem I told you that the bigger furnace size means the flow across the entire furnace, maintaining the same amount of velocity to produce fluidized effect is not yet achieved. So we are going step by step. So now we are 150 megawatt, 200 megawatt, up to 150 megawatt we have produced. We have now our target will be to go for 200 to 250 megawatt.
Okay, sir. Thank you.
Thank you for your question.
Thank you, sir.
Okay. If there is no more question, can I leave, madam?
Yes, sir. Yes, sir. Sure, sir.
Okay, I'm leaving. I'm giving my best wishes to all of you. And again, I tell you that these are very interesting topics, particularly in relation to the present day scenario. Energy is something which you cannot ignore. Sustainability is something which you cannot ignore. And when these two are matching each other, when they are marrying each other, so it's something which is really interesting. So in case you have any question later also, you can ask me. I shall be available, and it's a pleasure to whatever I have, because my age is around 70. So whatever I have learned, if I can, in my long career, if I can pass over something to younger generation, I will feel it a big blessing for me. Thank you.